Hi, welcome to the fourth session in the Hadoop tutorial series. I'm Ajay, and today we are going to discuss about MapReduce. The practical demos of MapReduce uses HDFS heavily. Hence, the prerequisite to this video is the previous video on HDFS. So please watch that first if you haven't. So currently we are looking at MapReduce, which is used for executing the user-defined operations on the data. For example, if you have students' marks stored in HDFS and you want to find the average of students' marks, then MapReduce needs to be used. So HDFS is like a file explorer for moving data in and out of Hadoop, whereas MapReduce is used for performing some operations on the data in HDFS. We will learn MapReduce with a simple example. MapReduce is made up of two parts, map part and the reduce part. Let us take a small example. The table which you see is the student's data present in HDFS. The first column, class, is the level in which the student is studying. This can be level 1, level 2 or whatever level. Also we have name and gender of the student and the total marks he scored. Now my objective is to find the average of students' marks in each and every class. If I were to do this in SQL, then this would be the SQL query. Now let's compare this with MapReduce implementation. In MapReduce, the reducer does the aggregation operation and the mapper does the group by operation. So first the mapper groups the data and then the reducer aggregates the data grouped by the mapper. That's all. Let's understand the execution process of MapReduce. Assume that the students' details are distributed among the nodes of the cluster highlighted by this red band. When the user submits the MapReduce code for execution, the mapper code goes to the system where the data is present. In our case, the mapper code does the grouping of students' data by each class. So the grouping gets executed where it groups the data in that particular system based on class. Now the grouping is done only locally. For example, the class 1 data might be present in all the 4 systems, and the mapper executed in a particular system would have grouped data in that particular system only. Now all the data with the same group needs to be combined for aggregation to happen. So that would be the next step. All the data with the same group moves to the same system and the reducer code gets executed in those systems and the results is returned to the client. Let's look at another small animation to become even more clear with this concept. Let's consider the same average of students' marks example using MapReduce. Assume that the 3 rectangles you see are the 3 nodes in the cluster which contains the students' data, which we had seen. The red blocks are the class 1 students' data, green blocks are the class 2 students' data, and the yellow blocks are the class 3 students' data. As you can see, all the 3 class students' data is present in all the nodes. Now the mapper gets executed in all the nodes where the data is present. In our case, the mapper groups the data by class. So as you can see, mapper has grouped the data in each node. It can be observed that the class 1 data represented by red block is still present in 3 different systems. So we cannot find the average of class 1 students' marks unless we have all the class 1 data in a common location. So that's the next step. All the class 1 data goes to a common node where the reducer will be executed to find the average. Similarly for class 2 and for class 3 as well. So here all the data which belongs to the same group goes to the same reducer. And this step is called shuffle and sort. Now the reducer finds the average and returns the results. All the data aggregated by the different reducers are combined and returned to the client. So this is how MapReduce works. When working with MapReduce, everything is in terms of key value pairs. We had discussed that first the mapper is executed, which groups the data, and then the reducer executes on the output of the mapper for aggregating the group data. Well, the input of the mapper, output of the mapper, input to the reducer, and output of the reducer are all in terms of key value pairs. Let's now see what the key and values are. Let us consider the same student detail example. When the program is executed, the first step would be the data being sent to the mapper. The mapper reads the data line by line in terms of key value pairs, where the key is the character offset of the first character of the row which is being read. The value is the entire row itself. In our dataset, for the first iteration, the first row is read by the mapper. Assuming that the data is present in a CSV file, the first row would look like the one which is blinking. The characters are counted from 0. So the key for the first iteration would be the first character offset of the first row, which is 0. And the value would be the entire row itself. Now if you count the total number of characters in the first row, you will find 8 characters. At the end of the line, there is a new line character, which makes a total of 9 characters in the first row. So the first character offset of the second iteration is 10. And since there are another 10 characters in the second row, the first character offset of the third iteration is 21, and so on. The user writes the mapper program. The program output should be such that the key is set to the group by column, which is the class column in our case, and the value should be the column that needs to be aggregated, which is marks column in our case. So the output of the mapper would look like this. Chances are that each set of output from the mapper may arise from different nodes, since the mapper gets executed in the node where the data is present. After the shuffle and sort, all the data which has the same key goes to the same reducer, and hence the input to the reducer looks like this. The user needs to submit the reducer program. In our case, the reducer is used to find the average of marks. As already mentioned, the output of the reducer is also in terms of key value pairs. Here the output key is the group by column, and the output value is the corresponding aggregated value. MapReduce is capable of doing much more complex operations, but this simple example of group by and aggregate is explained with MapReduce to understand its backend working. Now we will see how map and reduce process are invoked. Consider a data center with 3 racks. As we had already seen, a rack is a collection of data nodes connected over LAN. The communication within systems of the same rack is extremely fast. Assume that each rack contains 6 nodes. In this simple animation, the green block represents the HDFS data and the blue block represents the mapper task. If the HDFS data is present in a particular node, then Hadoop tries to invoke the mapper in the same node. This is the most optimized way of execution because we are preventing the loss of time due to moving of data from one node to another, and this is called data local execution. But there are situations when all the resources required to execute the mapper in that particular node would already be in use. In such cases, the mapper gets executed in a different node within the same rack. In this case, the data is transferred to the node where the mapper gets executed. This is comparatively slow since there is movement of data within the nodes. This is called rack local execution. There are certain situations where all the nodes in a particular rack are occupied with some other processing operation. In such cases, the mapper gets invoked in a node which is present in another rack. Since the transfer of data between nodes of different racks takes a very long time, this would be the least optimized way of mapper execution, and this is called off-rack execution. So, MapReduce is a programming model for data processing. It works using divide and conquer, where it divides the processing across many systems and conquers or executes it parallelly. When writing a MapReduce program to perform a certain operation, the user doesn't have to worry about how to process the distributed data. The user needs to write only the logic of the program, in our case, finding the average. MapReduce will take care of the complexities involved in executing the program on the data that is distributed. Since the program can be executed across thousands of systems parallelly, there are chances that the execution might fail in many cases. In those cases, MapReduce would re-invoke those failed processes until it succeeds. Hence, it will take complete responsibility for status and monitoring. Similar to HDFS, MapReduce also works on master-slave architecture, which we are going to discuss next. As far as MapReduce is concerned, there are two main processes. One is job tracker, which is the master, and the task tracker, which is the slave. When a MapReduce program is submitted to Hadoop, it is first sent to the job tracker. Job tracker identifies the location where the data for processing is present and then instructs the task tracker to invoke mapper in that particular node. Based on the instructions from the job tracker, the task tracker invokes the mapper or reducer program. There is one task tracker service running in each data node. For the analogy, job tracker and task tracker are similar to name node and data node in HDFS. Let's look at the duties and responsibilities of job tracker. It schedules tasks to be executed on slaves, which are the instructions to the task tracker. It is a very difficult operation since it needs to decide on the most optimized execution plan for the mapper and the reducer task based on the location of the data and the availability of the resources. Once the mapper operation is over, the reducer needs to be started. Job tracker takes care of this coordination. It keeps record of the progress of each mapper and reducer job. If any of the mapper or reducer job fails, then job tracker would reschedule it. Since it is the master and is the anchor of every MapReduce task, it usually executes on a powerful server like the one which executes the name node. Let's see the operation of job tracker. It is the process which actually executes the task by invoking the mapper or reducer as instructed by the job tracker. It acts as a slave in the master-slave architecture of MapReduce. It runs on all the data nodes. It invokes two other jobs, which are mapper and the reducer. It sends the status report to the job tracker regarding the mapper or reducer task currently being executed. Let's understand the working of job tracker and task tracker with the help of a small animation. Let's assume that the student's data for processing is distributed among 3 data nodes. The data is represented by 3 different colors: yellow, blue and brown. When a user submits a MapReduce code for execution, it is first sent to the job tracker. Now the job tracker analyzes the code and figures out the location of the data for the program to execute and then instructs the task tracker in those data nodes to trigger the mapper code. On instructions from the job tracker, the task tracker triggers the mapper code. The mapper then makes use of the data in that particular nodes and generates the key value pairs. Then the shuffle and sort phase takes place, where all the values with the same key goes to the same reducer. Now the reducer is invoked for each key. The reducer now works on its data and returns the aggregated output. It is to be noted that there will be one output file for each reducer. So if there are 3 reducers being executed, then there would be 3 output files. The user can specify the number of reducers to be used to get the job done. Now let's see how it works when there is a single reducer being executed for all the groups of data. Now assume that all the data is present in this data node. Similar to the previous case, the mapper and reducer program is submitted to the job tracker. The job tracker instructs the task tracker to invoke the mapper code. On instructions from job tracker, the task tracker invokes the mapper task. The mapper then makes use of the data in that particular node and then generates the key value pairs. Now the shuffle and sort phase happens. Well, in this case, since there is no data getting shuffled across the systems, and hence only the sort happens based on the key. Now the reducer is invoked in the same system. This reducer takes turns to handle different groups of data. The reducer first works on all the values with the first key, aggregates its values and then returns the output. Then the reducer works on all the values with the second key, aggregates its values and returns the output, and so on. It is to be noted that in this case the output of all the keys is present in the same system. This is due to the fact that there is only one reducer that is being triggered for all the groups of data. Let's review the MapReduce operation. After the mapper operation, there's a huge movement of data across nodes in the cluster due to shuffle and sort operation. This is a major issue especially when dealing with large data sets. We can solve this issue with something called combiners. We have already seen the operation of MapReduce, so I'm not going to reiterate this animation again since we have a good understanding of it now. The operation that we want to perform now is find the sum of marks of students in each class. Please note that we are trying to find the sum of marks and not the average as before. So the output of the mapper is the group data grouped by the class. Now the output of each mapper is given as input to an intermediate reducer which executes in the same node. In this case, the reducer is responsible for finding the sum of marks of students for each class. In this case, the output of each reducer is the total sum of marks of each and every class data in that particular node, which is merely a single number which is very small in size. Now this result needs to be combined again by shuffle and sort and then given to the main reducer for the final output. It is very important to note that in this case there is very little data to be transferred during shuffle and sort as it has been aggregated by the intermediate reducer. This intermediate reducer is called combiner. Let's get started with MapReduce programming. The prerequisite is a strong understanding of Java and object-oriented programming. I'm assuming that you have gone through my previous video on HDFS. If not, please check that first since we'll be using HDFS to a great extent over here. This is the students' data that we have been discussing so long. Image on the right is the data present in CSV format. The CSV is fed as input to the mapper program. This is the mapper code. There are few libraries involved in building the mapper program. Instead of int, long, string, Hadoop makes use of classes like int writable, long writable and text. There are many functional reasons for doing so which I am not going to discuss now. So we import those packages along with the package which defines the mapper function. The mapper code is defined in the map function. And this is the logic that we want to implement for our students' data to find the average of students' marks. Map function is defined by the mapper class and hence we inherit it. And then we override it with our logic. The sequence of Java generic for mapper classes key input data type, value input data type, key output data type, value output data type. The key input to the mapper is long writable because it is the character offset of the first character of that particular row. Usually the dataset contains billions of records and the character offset needs to be sufficiently large and hence it is long writable instead of int writable or any other class. The value input is text because it is the entire row data which is string data. The key output is text. Well, this can be anything since it is what we are sending as output. In our case, it is the class column and I set it as string. And the value output is int writable because in our case it is the column that needs to be aggregated, which is the marks column, which is an integer here. The map function takes 3 arguments. The first 2 are key input and value input and the third one is the context. The map function is called once for every row. So if there are 1 million records, then the mapper function is called 1 million times for each row, where the key input is the character offset of the first character of that particular row and the value input is that row data. The actual logic of the mapper program is just 2 lines in our case. The first line splits the CSV file into an array of strings and the second line extracts only the marks column and converts it into integer. Then we write the output of the mapper in terms of key value pairs, where key is the class column and the value is the marks column. Now let's take a look at the reducer code. Similar to the mapper code, the reducer also imports some basic packages. The reducer program is written inside the reduce function and this is the entire reducer program. The reducer function is defined in the reducer class. and hence we are inheriting the same. Similar to mapper class, the sequence of Java generics for reducer classes: key input data type, value input data type, key output data type, value output data type. The key input and value input of reducer is obviously the same as that of key output and value output of the mapper. The key output is the class of the student, which is here defined as text, and the value output is its corresponding average of marks, which is an integer here. Would have been better if it was float, but that's fine. Similar to map function, the parameters of reduce function is key input, value input, and context. The reduce function is called once for every key. So if there are 3 unique keys, then the reducer function would be called 3 times, and every time it is called, that particular key and its corresponding values are sent as input through its parameters. The for loop in the program simply adds up the values for a particular key. The average is calculated in the line following the for loop. The result of the reducer is written back to the disk in the form of key value pair, where the key is the class and the value is the aggregated marks. Apart from mapper and reducer class, there is yet another class which is used to configure the execution, and this is called the driver. This is the driver code. It takes a couple of libraries. The main function is defined in this class, and this is the entire code for this class. Job class allows the user to configure the mapper reducer job, submit it, control its execution, and query the state. When we run this job on a Hadoop cluster, we will package the code into a jar file which Hadoop will distribute around the cluster. Rather than explicitly mentioning the name of the jar file for execution, we can pass a class in the jobs set jar by class method, which Hadoop will use to locate the relevant jar files by looking for the jar file containing this class. We can set name for the job so that we can check its status later with that name. We need to specify the mapper and reducer class for execution. This is the reducer output key data type and reducer output value data type. This specifies the location of the program input file, which is the student's data, and the location where the result of the program is to be stored. In this case, the input and the output is set to the command line inputs, which is given during the code execution. This code makes sure that any other file with the same name as that of the output file in the output location is deleted. This optional line is used to set the total number of reducers to be used. This line calls for end of execution and returns the execution status. In our case, combiner does the same job as that of reducer. If you'd like to implement combiner for our use case, then create a new class for combiner inheriting the reducer class and override the reducer class as seen before. The main function should contain an added line to map the combiner class as shown. Now we will see how to execute this piece of code. 2 things before we start. First, download and install Eclipse on your system. Second, download the MapReduce program available in my GitHub link. This is the link. This link is also posted at the end of this tutorial just in case you miss it. First, we need to create project in Eclipse. For the same, open new Java project in Eclipse. Choose execution environment JRE as Java SE 1.7 while creating the project. Next, we need to add reference libraries. The jar files are present in the MapReduce GitHub repository of mine. Right-click on the newly created project, choose Build Path, configure build path, libraries, add external jars, then select all the library jar present in Hadoop_jar folder, then choose apply and close. Next, you need to place the code inside the project. Copy MapReduce code, which are 3 files present inside mr-avg folder in my GitHub repository, and paste it inside source folder of the project. If you paste it, it will automatically put inside default package. Hadoop requires the Java code to be submitted as jar, so we will export the project as jar. For the same, right click on the project, export, jar file, browse the location where you want to export, then choose next, select the class which has the main function, then click on finish. I have saved the jar file in desktop inside this MR folder. Once you download my MapReduce GitHub repository, it would contain the following files. Inside this source folder resides the student's source data. I'll copy this file to MR folder present in desktop. Now this MR folder contains the source file and the jar. For executing the MapReduce code, we must first move the code and the source data to HDFS. We have already discussed during HDFS tutorial about how to achieve it. We first move code and data from Windows system to a node in the cluster, and then from the node in the cluster to HDFS. To move the data from Windows to node in the cluster, we can make use of WinSCP. Now I am opening WinSCP, connecting to the server, navigating to the location, and now transferring the data. For transferring from cluster node to HDFS, we will make use of putty to execute HDFS commands. Now I'll open putty and connect to the server, copy the source data from local server to HDFS using the command copy from local. So the entire code would be Hadoop fs -copy from local, and you know that it takes two parameters. The first parameter is the location of the file in the local server in the cluster, and the second parameter is the destination. So I'm giving both as MR. So the source file is MR and the destination file is MR. Now let's check for the folder using the command Hadoop fs -ls -r. So this would check in recursive manner. Now we can execute the MapReduce jar file in putty by running the jar file. The command to execute the jar file is Hadoop jar followed by the location of the jar file. So it is mr/first.jar. Then it takes two command line arguments. The first command line argument is the location of the input file, and the second command line argument is the location of the output file where you want to store the file. So the first command line argument I am giving it as mr/avg.csv, and the second command line argument is output. So the output would be stored inside a folder called output. So it's going to take some time for it to complete the execution, so please be patient. Then you can check the contents using Hadoop fs -ls -r command. Now this is the output file. We will now check its contents. Hadoop fs -cat followed by the location of the output file, and now you can see that there are three classes and its corresponding average of marks. There are much better alternatives to MapReduce. For example, Spark, which is said to be faster in execution and easier to use. MapReduce programming needs to be done using Java, which is a bit pain. Alternatively, you can use Pig, which makes use of its own language called Pig Latin, which is comparatively very easy. And another alternative is Hive, which is much like SQL. Alright, now we are done with MapReduce. The next and last part of this tutorial series is about Yarn, which completes the essentials of Hadoop. It will be very encouraging if you can like this video. If you have any doubts, you can message me on LinkedIn, the link which is shown on the video. You can get the MapReduce code from my GitHub repository that can be found in the link shown. Hope you guys enjoyed, and thanks for watching.